So now we will cover process address space. Process address space is a fundamental concept in operating system that defines the logic memory layout for each process. It includes different segments for code, data, stack and heap, allowing processes to operate independently while managing memory efficiently through the operating system. So here we have a question, why is it important to understand? Understanding process address space is essential for anyone involved in software development, system administration, or IT infrastructure. It lays the foundation of efficient programming practice, security measures, and effective resource management in modern computing environment. Let's look at three key issues that highlight its importance. First, we have the challenge of not enough memory. Next is fragmentation. And the last one is security. So here we will talk about not enough memory. This is the range of memory addresses that a process can use. The CPU manages access to this space with each process having its own isolated address space. The blocks 0 byte, 1 byte, 2 byte are represent how memory can be allocated within this space. The slide suggests that as a process requests more memory, it starts at a smaller size and can grow until it reaches the maximum allowable size for that address space. The reference to 2 to the power 32 minus 1 bytes indicated that this system is discussing a 32-bit address space. A 32-bit system can theoretically address up to 4 GB of memory. As the process allocates more memory and approaches this limit, it runs out of addressable space. Once the process requests more memory than the CPU can provide within its address space, the system crashes because there is no more room to map additional memory address. So here we will understand memory fragmentation. So here we have different applications taking up various amounts of memory in the system. The 5 MB blocks represent free memory available for new applications. App1 and App2 have been allocated memory as required, while free memory exists, but it is not continuous memory block. Fragmentation starts to form as memory is allocated and delocated. Even though there is technically enough free memory, but App3 cannot use it due to the lack of a continuous block large enough to fit its requirements. This illustrates the concept of external fragmentation, where memory becomes shattered into small and unusable blocks. The process address space allows the system to allocate non-continuous block of memory to App3, overcoming the fragmentation issue. This prevents memory wastage and allows efficient usage of fragmentation memory. So here we will cover logical address and physical address. Logical address is the address used by a program to access memory. From the perspective of a process, the entire memory it needs seems to be continuous and private, forming a unique logical address space. These addresses are used by the process for instruction and data, but are not directly mapped to the physical memory. A physical address is the actual location of data in the computer's memory. The physical address space represents the real memory installed in the system. Multiple processes share the physical memory and the operating system must manage access and allocation of physical address to process. This slide is a virtual demonstration of the key difference between logical and physical addresses. It is crucial for understanding how memory is allocated and used by a process in an operating system. The logical address on the left hand 100 for process 1. From the perspective of process 1, it requests memory at logical address 100. This is a virtual address that the process believes corresponds to its memory. The physical address 1000 on the right, in reality the memory is stored in a different location in system's physical memory. In this case, the logical address 100 is mapped to physical memory 1000 by the memory management unit. In short, whenever the process needs to access the data at logical address 100, the MMU translates this address to the physical memory location at 1000, making the memory access possible. We have seen how a single process maps its logical addresses to physical memory. Let's explore what happens when multiple processes are running on the system. Process 1 and process 2, both processes have their own logical address space. Notice that they may have the same logical address. For example, both have a logical address 100. These addresses are isolated and unique to each process. Logical addresses do not conflict even if they are the same across process because they are in different process address space. Although process 1 and process 2 have same logical addresses are mapped to different physical addresses by the operating system. For instance, process 1's logical address 100 might be mapped to physical address 1000, while process 2's logical address 100 is mapped to physical address 1600. The MMU ensures that each process logical address are translated to the correct physical addresses without overlapping or interfering between processes. The separation is crucial for ensuring process isolation. The operating system ensures that they do not interfere with each other in physical memory.